Ok. Pessoal, boa tarde, bem-vindos então a todos ao nosso seminário de mecânica. É um prazer tê-los aqui conosco nessa tarde de quarta-feira, tá bom? Hoje a nossa palestrante é a Lydie Staron, da Institut d'Alembert, da Sorbonne Université de Paris, e ela vai falar para a gente sobre simulação de materiais granulares coesivos. Aquele lembrete de sempre, por favor, se você não quiser ser visto ou ouvido, desligue seu microfone e desligue seu vídeo, porque essa palestra será gravada e vai ser publicada no YouTube, tá bom? Lydie, I just said a quick announcement about our rules and how to behave. As I told everybody, you are our speaker for the afternoon. Thank you so much for accepting our invitation. It's a great pleasure to have you here. As I said, this is a very informal seminar, so people can raise their hands and ask at any time questions. I think we've discussed that already, right? And it's fine with you. So without any further delay, Lydie, please go ahead and start your talk. Thank you once again for accepting our invitation.
Okay, it's fine. Thank you for inviting me. And sorry, I'm not very familiar with Teams, actually. We are using Zoom here. And anyway, I haven't given a talk using directly face-to-face to my computer. Usually I don't talk to it. Anyway, I'm going to talk about simulating cohesive granular matter and going through stability problem, and if we have time, pattern and failure issues. I'm familiar with granular matter in general, but not cohesive one by no means. So I'm showing what I know, and I thought maybe I could start my short introduction with looking for a definition. So I typed cohesion on my favorite engine. What came out actually is not really relevant to my talk, but it just told me how much you can forget about the primary meaning of a word focusing on scientific issues. So anyway, a definition that came out was the sticking together of particles of the same substance, which I agree with, but for the same substance. I mean, I'm not aware of any such condition. So what I consider is cohesion is just tensile forces at contact between fragments or grain in a discrete system that will oppose the system deformation. So I think you probably agree because it's a very basic definition. So these tensile forces actually happens very often in small grains where you have van der Waals forces. They also mess up with many experimental settings, actually, where electrostatic contacts are created whenever you have plastic elements in your experiments. And of course, the most common case is capillary bridges, which are immensely used in experimental settings of cohesive granular matter. So this translates at the system scale by the existence of a yield stress, which of course stability limit problems, viscous-like flow behavior at low cohesion for which a flow actually exists, and the impeachment of a flow by aggregates and clogging at large cohesion. All these aspects are actually known, but not so much studied. So actually, cohesion is new to me as a subject for study, but it's actually an old problem because it's very, of course, it's intrusive in many industrial problems, where it might be a challenge for industry who wants to create agglomerates using cohesive contacts, or a nuisance where it prevents the flow of powders and where abstraction can happen in a silo and such devices. So the phenomenology is actually known, but there is little research that allows for a theoretical link between what is observed and what we know of cohesive contacts. So it's also, of course, very present in geoscience, where most soils are actually cohesive and sometimes fail, as we see here in Peru, due to massive rains and the increase of pore pressure that has induced the loss of cohesion. So it's a tricky research subject because creating reproducible cohesion in the lab is not that easy. So experimentalists use usually water for creating capillary bonds through wetting or silicone oil. And only recently, sticky contacts were achieved using polymeric coating, which allows you to have all contacts cohesive in one system rather than randomly distributed capillary bond. Measuring cohesive force is also difficult. So most often dimensional analysis is used, using, for instance, surface tension and such things, and mechanical measurements are sparse, in fact. And it's also an issue which is not as expected, but it's also an issue in simulations, because in DEM, for instance, which is perfectly working fine in a non-cohesive situation, stiffness and damping, which are the basic ingredients of the algorithm, are mixing up with cohesive forces. So cohesion is no longer a single well-identified physical ingredients, but it becomes an effective an effective property where stiffness and damping, which should have nothing to do with it, are included. And the same occurs in contact dynamics, with time step, this time mixing up with the effective cohesion. So I'm not going to talk about this now, and but it's actually exists. I mean, numerics is not proof completely of this kind of issues, which are usually more concerning, involving experimentalists. So the outline might be a short stability analysis, which will be used later in the parts of showing the slumping of discrete granular piles and the part showing the slumping of continuum granular step, both allowing us to link the contact scale, the cohesion at the contact scale and the macro scale. And if we have time, I don't know when I started actually, but anyway, if there is time, I could show how to characterize the granular deposit pattern and see how it relates to the cohesion, and discuss the identification of a failure plane. Now, the stability analysis is actually 2 slides, so very short. It's just showing, just analyzing the stability of a corner over, a part of a rectangle sliding on a failure plane. So if it's cohesive granular matter, it's just obeying a simple rheology, granular rheology, with a yield stress τ in addition, with a friction mu, depending, of course, of the angle of friction. And we just write the equilibrium of the upper block, the yellow one, along the failure plane. And this block will be stable as long as the weight, or rather, as long as the friction and the cohesive stress are big enough to balance the weight, which tends to drag the yellow block downward. So you just write it's simple actually. Nothing crazy here. You just write the equilibrium of these three forces, and you end up with the height of the height of the corner being smaller than the function here that you see, which depends on the angle of friction phi and the angle of the orientation of the failure plane. And if you find the minimum, if you minimize this function, it gives you the highest height for which the block remains stable. So to do this, you have to just differentiate. It's not as if it was just that easy, but it's just you just differentiate the equation, find the zero, which gives you the angle, the orientation of the failure plane as a function of the angle of friction. If you have this, you just use it. You just replace alpha with this expression in the function here. Okay, and you obtain this expression readily with mu, the friction of the material. So mu here is a macroscopic property, is the property of the material, the friction along the failure plane. All right, so these are these two slides for the stability analysis.
Caio, do you want to ask something?
Hello, Lydie. I have just one question. What is the phi angle?
Yeah. Phi here is the internal angle of friction, and the coefficient of friction is the tangent of this angle. So it's just a material property. It's nothing geometrical.
Okay, I see. Okay, thanks.
Fine. So anyway, yes, this I'm showing here not just because it's mathematics and it seems relevant here, but we are going to use it to derive some quantities. You'll see anyway. So now let's go to the stability of discrete granular piles using the contact dynamics algorithm. Sorry. So here you have a schematic illustration of what the experiment is. It's just a pile of dimension H naught and R naught left to fall in the gravity. So here it's obviously cohesive because something remains inside like solid. The number of grain ranges from 100 to a few thousand. The mean grain diameter is D. The height varies and the basal radius varies. And of course, we allow tensile forces because we are interested in cohesive material. The simplest one that can be defined, but usually contact dynamics algorithm uses simple expression for the contact because it doesn't focus on the contact phenomenology. Anyway, here we are using an adhesive force which depends on the mean weight of a grain and is proportional to the bond number. So varying the cohesion means varying the bond number. So here we vary it between 0 cohesionless to 150 and see what it with what it coincides. And of course, there is a Coulombic friction in telling you, each contact, the tangential force is given by the Coulombic friction. And here the coefficient of friction mu c is a microscopic one, it's the contact one. It's not the mu one that you find here. Okay. So using this setup, we just see if we vary the dimension of a pile and we vary the cohesion and see what happens. So 3 examples are shown here for varying bond numbers between 50, 100, 150, and we see what happens. So 150 is cohesive, very cohesive. and the pile seems like stable, and for 50 it falls. I mean, it really collapses, fails completely.
Lydie, can I ask a quick question?
Wait.
So in your model, you assume Coulombic friction, so you don't use the standard, what we use in DEM, the Kundal history forces. Is it because of your algorithm, the contact dynamics algorithm, does not require Kundal-like forces? Or is it because you've chosen not to regularize anyhow Coulombic friction?
Okay, so I've decided not to show the details of the contact dynamics algorithm, but in the contact dynamics, actually, contacts are not explicitly modeled. It's just an implicit description, and the forces are not answering an explicit description and an explicit solving, but the solving is implicit. So there is a convergence loop in which actually only Coulombic friction is just inequality. Actually, you just know that the tangential force will be smaller than the normal force times the friction.
I see.
It's just one condition,
I see.
which is enough to solve a set of forces, and the solution is not unique. So it's discussion is actually it's a whole seminar about it.
Okay, I see.
So,
and if there is slip, then it's just dynamic friction.
Okay, you can do this. You can just change this coefficient of friction from when it slips, deciding that the friction is suddenly lower, for instance.
I see.
Okay, but you don't have to. I mean, the main ingredients is just that it's dissipative.
I see.
So we don't know the details. Okay.
Okay, all right.
So anyway, so here in this example, you just see failing piles and static pile, but in black you see, in dark you see the grains and gray you see the grains which have had a motion. Sorry. So it's nice. What we need is quantifying the slump, which is not that obvious. So here, for instance, you see the pile slumping for 4 values of, or not slumping, or not falling actually, for 4 values of the bond numbers. So you may check how far it went and decide this is a criteria, or see how much it fell down. So this is the mean height of the grain, which tell you this, or just compute how many cohesive bonds were lost and see what it tells about the slumping. Here in the following, we have just decided to make a geometrical description, computing delta x and delta y, which are just the amount of horizontal and vertical distances, travel during the slumping compared to the initial position. So and this is computed for the 2 actually secondary center of mass. So here you see this is my system, and you can define 2 centers of mass because the system is completely symmetric. So it makes sense. And having this, computing this and changing the size of your system, the height essentially, and the bond number, then you can plot, plot how much the pile deformed. All of them actually, you just plot all your points, and you see essentially 2 clouds, one cloud that would coincide with small displacement, and one cloud that coincides with large displacement, which tells you who is unstable and who is stable, and few points in the middle who certainly coincide with the non-symmetric slumping, meaning a pile is just slumping, failing on one side, and on the other side is fine. Okay.
This is due to the intricate aspects of the initial condition, right, Lydie? If you chose another initial condition, you would have something else.
Yeah, exactly.
Okay.
This will be a bit discussed later. Here is just a stability analysis, but it's true that in this specific study, I don't know, stability analysis, each run is each dimension. For each dimension, each microscopic dimension, there is one run only. While I could have done 10 runs for each and having error bars to show. Here I have no error bars. It's not that hard. But because the results are consistent, you don't feel like you need error bars to conclude. So anyway, and so we have decided that these points were stable, these were unstable, and those we'll see where they fall. But actually, these are fairly clearly stable, and these are fairly clearly unstable. So the stable are black here, the unstable are red, and you've plotted the height as a function of the Born number. And you can see a well-defined boundary between the two, which gives you an expression for the yielding height, the yield height, which is 0.45 bond. So, okay, the pies behave correctly, I could say. There's nothing fancy in their behavior. The question is, does it tell us something about the micro contact adhesion and the macro cohesive yield stress? Because here, because we are discrete, we have a microscopic contact force. We know it. I told you it's, a simple adhesive force proportional to the weight, but we have no yield stress. So you can always define a yield. In granular material, it's often the case. You define a yield by dividing by the diameter, which is a minimal surface. The contact surface is usually not known. But that wouldn't lead us nowhere, actually. So instead, we introduce a distance, a surface, a surface in 1D, because the simulation or 2D. Okay, I didn't say it, the simulation or 2D. I'm so used to it that I forget to say it. So we introduce surface A, which we use to define yield stress by simply dividing the force by this surface. This surface is a certain number unknown of grains diameter, but this allows us to define a yield stress and equivalently a cohesion length, which is just the yield stress divided by gravity times the density of the material. And doing this, we can thus propose the following transition between macro cohesion. This is just saying the yield stress is the force divided by the surface A. And using this, we can compare it with the analytical prediction given by the stability analysis, the first two slides that I showed at the start. But for doing this, we need a prediction for the mu here. So the friction that I put in the code is the friction between the contacts. So this is 0.5, it is known. The friction here is the macroscopic friction. So it's not 0.5. Having done many simulation even long time ago with these values, and having studied how much the contact friction influences the macroscopic friction, 0.3 for the macroscopic friction is extremely reasonable. So without having made the experiments which you need to do to really compute the macroscopic friction, we choose to put this value and we combine the two and we use the stability limit that we've here. We just use this expression, which is just given by the data. So we just write this prediction. We replace the yield stress by the expression as a function of bond. And we know that this yield height is equal to 0.45 bond because the data give us this. And doing this, we can have a measure, not a measure, but an estimate, a direct estimate of this mesoscale length that we have introduced, which tells you that the length is roughly equal to 9 grains diameter, which is a typical value for mesoscopic characteristic length.
Lydie, would this be the characteristic length of an aggregate? Or it has nothing to do with that?
I think it has nothing to do with this because an aggregate will really depend on bond, on the cohesion. And here, this mesoscale length is computed for any bond because it's given by a stability limit for any bond. This is true for all the bonds we have tested.
I see. Mm-hmm.
So you wouldn't be given by this. And okay, we can discuss this a bit later because
okay, all right.
When I'm nearly finished with this, right. I should talk about the problem of the size of an aggregate.
Okay.
Eventually, the link between microscopic and macroscopic cohesion is consistent. We found a bridge. Now the problem is, do continuum simulation approve of that? It's fine. I mean, we're in between us, it works. What if we see continuum stability? So now we assume a continuum equivalent. We use the mu of I rheology. So in cohesionless system, the mu of I rheology is just here. I mean, nothing more. Just you probably know the mu of I form. I mean, this is one form. Here, I'm interested in stability, so the I number will be close to 0, which means that the mu of I will actually just be a static friction. And so here we used the value given by Job et al. In their seminal work on the mu of I rheology, which is 0.38. So it's just a bit random, but we just took it from a paper for classical. This is a value which is classical for dry granular matter. And because we are interested in cohesive material, we supplement this rheology with a cohesive yield stress, which is where the cohesion is actually included. I mean, and this is what will be varied in the following when we want to vary the cohesion. So doing this, we are able to define an effective viscosity by playing a kind of a dirty trick, by just dividing the shear stress by the norm of the shear rate and multiplying again by the shear rate, which works fine. Actually, we did this without the yield stress some years ago, and it's giving very good results. and it's certainly, I mean, correct, very correct to do this in situation where the shear stress and the shear rate are close to be collinear. So defining this viscosity, we are able to implement it in a Navier-Stokes solver. So as it is the Basilisk code of Stéphane Poppinet. And it works. I mean, it works, of course, because the viscosity will diverge for, quasi-static motion. If the shear rate tends towards 0, this viscosity will diverge. So you need to introduce regularization, namely a maximum value for the viscosity. So here we see an example of a continuum cohesive collapse, showing the runout as a function of time. So this is the classical evolution that we know. Here we just see what is the influence of the eta max. Actually, it's eta max. Sorry. We are not really interested in this zone in stability issues. There is no creep motion, so the regularization is not important for us. And here are 3 pictures. I mean, 6 actually, but 3 stages of the slump, showing here the velocity, here the inertial number, and we see a well-defined shear zone with a very dynamical part falling away, and we see actually that there is a floating wedge which will be traveling down, which remains static. This is what is seen also if you do the same with the Bingham plastic, for instance. Now that we can do this, changing the cohesion and changing the initial height, we can map the stability of the system, so varying the cohesive threshold through varying the cohesive lengths within a range which is okay, which is just enough to capture the boundary between collapsing state and stable state. We can here test directly the prediction. We have the macroscopic friction, which is the one that is really this time microscopic friction put within the model, in the model through the rheology. We just write it down here and it gives you this. So it works perfectly. I mean, a bit, well, okay, it works. Can we compare this with discrete collapse stability? So we can actually, using the relation we've done between microscopic contact adhesion and macroscopic cohesion. So here the cohesion is plotted in terms of the cohesive lengths. So we just translated the discrete simulation using this expression, which allowed us to plot on the same graph the discrete and the continuous data. And we see that they fall within the same areas. And this is actually this line, the same. So the agreement between discrete and continuum is surprisingly good, using no fitting parameter, and there's only one very reasonable assumption for the discrete matter, which is the value of the macroscopic friction. There is no fitting parameter, but for the fact that we're actually using parameters for the continuum simulation that were published long ago, actually. I mean, long ago, 15 years ago, which is long ago. And who coincide with classical dry material. And I've been using classical quantities for simulating the discrete contact dynamics granular. So there's no fitting parameter, but we've been using similar rheology. So if one of us, I mean, if either the continuum, either the discrete had used completely different friction, completely discrete friction, actually, that's the only points that here can make a difference. Certainly, we wouldn't have such a agreement. Anyway, we're happy with this. So to conclude, the simple rheology we've implemented in continuum Navier-Stokes solver is enough to capture the continuum stability behavior. The main ingredient is actually the yield stress here, because that's where the cohesion is encapsulated. We haven't supposed that the friction mu is affected by the cohesion, but it could well be the case. This has not been, as far as I know, this has not been studied in a systematic way. So we've evidenced the relation between discrete, micro, and macro cohesion, and stressed the important role of mesoscale lengths in the computation or the estimation of macroscopic properties. So the discrete and continuum compare well when we are interested in stability, but the subsequent flow is very different, actually. So I thought I might talk about deposit patterns. These are short parts now. I don't know if I have time.
You can carry on, Lydie. You started at 20 past, so you still have some time if you want to.
Okay. Okay, I want to. So deposit pattern is what I mean deposit pattern, because it's a small deposit. It's just the deposit left by the angle which has fell down. So here you see continuum simulation, here the discrete. So the two first, the four first pictures are the earlier moment of the failure. We see that the failure plane are essentially consistent. The shape of the falling pile is also consistent, but the final deposits are very different. So here we see a smooth surface, while here we see a very rugged profile. And the stable corner, which is, okay, here this is the initial state, so it's similar. But when the corner falls down, it falls down here too. We can see it. Probably you can see it too. And here, once it falls down, it's completely crushed by the flow. I mean, although it's not a very rapid flow or a very with important motion, anyway, it's crushed and it no longer exists. While here, it outlasts really it survives the flow. So obviously, we here have something which we cannot study otherwise. I mean, only experimental studies of real granular matter or can give us clues about the way this roughness is decided. So experimental or numerical, because I don't do experiments. So therefore, we've performed a series of 66 simulations with a constant number of grain. This is not varied. The dimensions of the system are not varied too, and they are high enough not to be a very squat system, but and high enough to fall actually, because if it's too okay, high enough, so it's dynamical anyway. So for this height, we use cohesion, which coincides with a slumping situation, with the bond numbers from 0, namely cohesionless systems, to 50, which is the maximum bond number for which a flow was actually happening. So here we see the final state achieved by the system for a cohesionless system. So this is the usual deposit that we observe anytime a dry granular material falls, namely a smooth slope. Here the slope is less and less smooth, and at the end we have a very dirty deposit actually. So here we know, because we've observed it a lot, that this will happen anytime for any system. And this, from the shape, we see that this is probably not very reproducible. So in addition of varying cohesion, we also varied the initial state. So the initial state, we vary it only by simply by varying the way the grain diameter are distributed in the system. So it's just the very microscopic structure, of the system that makes the difference. So here you see six example for a fixed bond number of 30, and we leave it to fall under gravity normally. They are the same, and we see the results are similar but different. So we need a statistic here. So
Lydie,
yeah.
I have a question here. Can I? So there are two questions actually. The first is, can you? I don't know if you had said this already. I didn't understand. Can you validate these bone numbers experimentally, or are they just a computational workaround for you? Is it able to? Are you able to go into the lab and see if a certain granular matter that you're studying has a bone number of 30, for example?
Okay, so as I said but very shortly in the introduction, there are very sparse mechanical measure of contact forces. The bond number here, which I'm using, so I haven't made up this adhesive force myself, is just an analogy with the forces applied in droplet issues. So it's from fluid dynamics, and it's used because it's convenient to compare a cohesive force and adhesive force to the weight of the two grains in contact.
I see.
If you could have, because people start to measure this now on a very tiny scale, because you're trying to measure experimentally contact forces. If you measure contact forces, you just measure a force.
Yes.
Now, if you measure this force for, I don't know what you vary in the experiment, but you measure this force and you just plot it and normalize it by the weight of the grain, this will give you a bond number if you decide to give this expression.
Right.
Then the choice.
Right. Makes sense. The other question is, can you, so for example, in these simulations that you're showing right now, you just have a one-sided collapse of the granular bed, right? But in the previous ones, you were showing a two-sided collapse, right? Yeah. So is it expected that you will have the same results for one side of the two-sided collapse as you're showing right now? For example, if you took off the wall that you're showing in the simulations right now, is it expected that you have a symmetric pattern that does not influence the other side?
So now I'm showing bonds of 30. So for such a small cohesion, if I remove the wall, certainly the other one will fall. If I'm using a larger bond number for which stability is possible, I mean just possible, not necessarily achieved, but possible, then you don't know. One side may fall, one side may manage to remain static.
I see.
But this depends on the height. These are high, I mean, okay.
I see.
It depends on the bond number that you're considering, respective of the height.
I see. Thank you. I think that.
And the boundary condition also changes, right, Lydie? Here you are having a rigid wall that has wall particle friction, and in the other case, it's particle friction.
Here it's particle, I think.
But you prescribe that the particles are fixed at the wall.
Yeah. Yeah, they're fixed, and the coefficient of friction is the same as, and the cohesion is the same also.
It's the same.
They are also cohesive. Otherwise, there would be slip motion.
I see. Okay.
But the idea here was to be able to have a failure plane. So, sorry, I just go here to have a failure plane even in the cohesionless case, which would be far enough of the wall so it wouldn't be affected. But this wall is not meant to be seen by the deposit.
Yeah, agreed. Yes.
Okay. So anyway, so what we've done for each bond number 11 runs to have a statistic about the roughness size. So here you have 3 cases showing the final profile for cohesionless system, a cohesion with a bond number of 20 and here a bond number of 50. You see in pale blue the profile individually of each simulation, and in dark the mean profile. So here we can see that it's noisy. I mean, you can see that the mean is quite different from each profile individually. For cohesionless, they are just the same. So we just evaluate the profile fluctuation by subtracting the mean value of the profile to each profile for each horizontal position. And we characterize their typical size, computing the the standard deviation. There's no other. It's just a simple standard deviation, which gives you the typical size. So if you plot this typical size as a function of the bond number, you obtain this. In the case of cohesionless system, you observe that the typical fluctuation size is just half a grain diameter, which makes sense because when you see the smooth profile, you just see half of a grain every so often coming out of the mean evolution. And you see also that for a larger, the larger the cohesion, the larger the error bars. I mean, the fluctuations are actually not as well defined and they are bigger. But irrespective of these details, each one by each one, you have a neat correlation between the fluctuation size, the mean fluctuation size, and the bond number. So these are a fluctuation of the vertical size, actually. What happens in the horizontal direction. So for the horizontal direction, we had no mean but for calculating a correlation function, which is given here. So this correlation function gives you the typical correlation length, which is given by so here actually you can see the shape of this correlation function. So here for a large bond number, for a small bond number you see nothing, it's flat. Okay, but for a large number you see what it looks like, and the maximum gives you actually the characteristic length. I mean the corresponding correlation length.
So sorry, Lydie, I don't understand this. Sorry, this is not the run out. This is just the structure in the horizontal direction of the surface.
Yeah. So ideally, you have it could be the fluctuation of the line along the final slope, for instance, but you cannot define a slope for something like this.
Yeah, I mean, I see.
You cannot at this stage, but yeah, it has nothing to do with the run out. It's just this shape. So we do not consider this. It's just the black, the profile of the black grains.
Okay.
And so here we just computed the typical correlation length of the profile, and we plotted it as a function of the bond number, and we also see a nice correlation. So this shows, and that's all I mean, it's actually a very preliminary study. It's we are doing it now. But the spatial distribution of cohesive blocks seems to be a direct picture of cohesive forces. And to come back to what you were asking earlier, Yuri, for the size of the aggregates depending on the cohesion, certainly to answer this question, we need to better understand these data that I'm showing now. So it's a direct picture of cohesive force, but it doesn't need to be the only one, because the slump will also be affected by the dynamics, actually. I mean, the profile will also be affected by the dynamics of the slump, so by the initial height. So this is not studied here. I mean, it's another study, actually. And the question is also how much it departs from the failure plane, because when you start the failing, and how much are you going to move compared to this? So this would lead us to the question of defining a failure plane, but maybe I've talked too much already now. No?
If you want to carry on, that's fine. If you want to stop, that's also fine. You decide.
How long I have been talking?
So you've been talking for 50 minutes now.
50?
Yes, 50.
Okay, that's enough. I'm just showing what it would be. I mean, actually, it will be published in Powders and Grains, so I don't really, if you're interested, you can look at it. It's just questioning how can we define and capture the failure. So it's just, okay. And this is it. I'm not showing. I think 50 is a maximum limit for a seminar.
Very good.
No, it's true. I mean, it's just talking, and nobody really is too tired to follow.
To anyway, get anything else, yes.
Yeah, exactly. So, okay. So, conclusion, I'm just repeating once more. We've done a stability analysis for a discrete and continuum granular pi, trying to link the microscale and the macro scale cohesive properties, either contact forces or macroscopic yield stress. And that's it. And then showing a preliminary study on the link between the morphology, deposit morphology, and cohesive properties. And in the future, we will try to better characterize the failure plane. And certainly that would lead to testing the more Coulomb theory, which is a big... Anyway, thank you.
Thank you very much, Lydie. Thank you so much for this very nice talk. And it was great. We've had many questions already during the talk, but anyone now who wants to ask a question, please go ahead. So before I give you the word, Teams is bugged up. I don't know what's going on. So Jorge, who just asked Lydie a question, is not appearing on the list. So I can't see raised hands. I can't see anything. Teams is bugged. So please just go ahead, open your mic and ask questions to Lydie, okay?
I just want to say hello to Lydie.
Hello, Albans.
It's I'm very glad to follow your talk and to see is very up to date in the issues in the granular material. Hello, Yuri, and just to make a question that Yuri already cited in your talk. How you expect any kind of difference if you use a kind of molecular dynamics code to simulate this kind of issues, or you see that everything will be the same? All your conclusions are independent of the simulation code, simulation method.
I'm pretty confident to say it's exactly the same if I'm not cohesive. I mean, non-cohesive matter is simple enough. So if they are rigid and the way they dissipate energy might be a bit different, but I'm pretty confident the macroscopic, the mean behavior is the same. For cohesion, cohesive systems, I cannot conclude now. Really, I'm really not sure.
And I'd like to question, you being the talks in Power the Grains in Argentina, you'll be there?
In
the powders and grains now in July, that will be online, of course, but it will be held in Argentina. You participate in the
I won't be in Argentina. I won't be in Argentina, but I will be on the virtual platform. If that's what it meant.
Very nice. So you can talk again in July. So thank you very much for your talk. Thank you, Yuri, for inviting me, and I'm very glad to follow this.
Very good.
Very glad to see you. Ciao, ciao.
Yes, yes. Very good, very good. Thank you, Albans. Any other questions for Lydie?
Yeah, hello, Lydie. My name is Gabriel.
Gabriel, go ahead.
If first, the cohesive force on your discrete model, it is constant for each particle, right? For each pair of particles.
Okay, what is constant is not the force, it's actually, I've been very quick on these more technical aspect. It's not the force which is constant, who is constant is the threshold. So the force can be cohesive between 0 and the threshold. When it reaches the threshold, then the contact is lost.
Okay, so
so
the particles are in a bounded state until you reach this threshold, and after that they are not neither in contact nor in bond anymore, right?
Yeah, exactly.
Yeah, that is something that Gabriel is my student, and we tried some time ago to do some molecular dynamic simulations of cohesive materials, and setting up the force and the link between two particles so that they remain cohesive and then separate. It's not trivial. And it's very different, right, Gabriel? You have to calculate at each time the force that you're applying to a pair.
Yeah, what we did, we had a constant force, and when the contact between the particles ceased, because the force was surpassed, then the bond is broken and there is no cohesive force anymore. So what you are saying is that you are keeping the particles fixed somehow until a threshold is met, right?
Mm-hmm.
So my contact is just acting as if it was non-cohesive, but when it is non-cohesive, if the contact is no longer compressive, it can open. So when they are cohesive, if the contact is no longer compressive, it survives actually. It becomes tensile. So there's the force, which is a cohesive force, up to a point where it has reached the threshold, in which case it opens. The same way then a contact would open if it was no longer compressive, but there is no cohesion, then it can just separate.
Okay.
Can you build? Sorry, Gabriel, go ahead. I thought
after after the bond separates, it can't form anymore, right?
Yeah, that was my question.
I'm not sure.
Once the bond between two particles is broken, can you form it again, or it is permanently broken?
You can form it again. They are sticky actually. This cohesion is a stickiness. It's just like you take like the coating they do experimentally. It means it's just sticky. So you open it, but you close it again, it sticks again.
So whenever there is a contact.
When there is a contact, it sticks. When it opens, it opens. But if it goes back into contact for some reason, it sticks again. It's not as if it was broken. It's not as if it was brittle material. It's not brittle. It would be brittle if you wanted to simulate a bond with some minerals, for instance, which have hardened. So it's glued. But then when you break the bond, it's broken forever. You cannot create for just like crushing material.
Yeah,
so
okay.
In my case, it's sticky. It's what usually is understood as cohesive material. It's just like a van der Waals forces. They exist as long always. They always exist.
Okay, thank you. That answers my question.
Very good. Does anyone have another question for Lydie?
Yuri, can I have a follow-up question on that?
Yeah, go ahead, yes.
Yeah, just for the contact force, the cohesive force, if before it reaches the threshold, is the force proportional to the distance of two particles? Like you have a stiffness, or what is it? How do you determine the force?
You don't, right?
There is no stiffness. Actually, the algorithm is not obvious, not that explicit algorithm are more obvious, but it's easier to understand the way we compute the force. I mean, you have a distance, and following the distance, you compute the force. This is explicit. This is a physical model for the contact. In contact dynamics, you don't have such a thing. So
the force can increase if the particles are setting apart. The force is increasing until they reach the threshold.
Well, no, it's not dependent on the distance. It will increase only the force applied to the two grains in contact is such that the tension in between the two increases. So it's only force dependent. So if you take two grains in contact, the way they will exchange forces, the forces between the two will only depend on the resultant of the forces to each grain, on each grain. I would really need an hour to explain this, actually.
Okay, yeah, I'll read the paper. I got the paper.
It's not explained on the paper. That you need to read the paper on the contact dynamics algorithm.
Okay.
So actually, I actually have written a very simple. I mean, it was meant to be very simple paper on contact dynamics algorithm, and it's published. It will be published on the ECOMAS conference website. I don't know. Anyway, I can send it to.
If you could send us the link, that would be great. Yes, or the paper.
Okay, just send you the paper.
Yes.
It's not yet published, but it's just. It was meant to be simple, so you understand the contact dynamics easily, because I know no one understands it. It's true. I mean, it's not my fault. It's not my creation. I mean.
Any more questions for Lydie?
Just another question.
Go ahead.
For me, please. So, for the bumpiness of the final deposit that you show, you said in continuum simulations you cannot capture that. Well, only you can see that in DM or experiment. So, have you considered how you can capture that actually in continuum simulation?
Anaïs, actually, which is the second author in this seminar, is hoping to find a way to capture this kind of what internal length or implicit length scale, and to find a way to implement it in a rheological model, but it's a hardcore science, if I may say. So
it's kind of an instability problem that has to be built in the code, like in the rheology model.
I'm not sure what it would be. I'm not sure what, but it's a kind of a model, a quantity that would create zero shear rate zones in the continuum.
Thank you.
Yeah, so following up on Lou's question and on my previous question before on the length, on the mesoscopic length. So if you showed us the very first picture, Lydie, of the landslide in Peru, you will see that there is a very clear length scale of fractures, of successive fractures on your deposit. So the first question would be, is there any connection? You see there on the second one, sorry, there is some sort of wavelength there, you see, on the second one. So first question is, do you think there is any link to this aggregate size, macroscopic size? And you said no already, to that mesoscopic length scale that you defined. And question number 2 would be, so on your simulations, you saw some of these features, but I think the small scale prevented you from seeing larger frequent events like this one you see. Do you think a larger simulation would be able to get that? And and then the question would be, can you do that in a continuum? But I think you already answered that to Lou.
So for the continuum, I cannot say very clever thing. For the first question, actually, it's not a bigger simulation that I need. It's just a very different simulation with a flow, actually, classical flow, free surface flow of cohesive material with boundary condition. So no limit in time, no limit or less limit in size. And we will see how the free surface develops length scale, the same length scale that you see here. So in the result that I showed for the pattern of the free surface, I said, of course, they depend directly of the cohesion. We can see clearly, but they also depends as much or maybe even more on the dynamics, namely on the height. And the problem is the dynamics here is transient. So it's very difficult to conclude, to make a definite conclusion. So I know some people have done experiments of flowing cohesive material, and they've registered the length scale at the surface. I don't have the papers, actually. I'm not. It hasn't been published for a long time, so
I see.
I cannot tell you exactly what this is.
This is. I see. Yes, please do. I have one more question, but before that, can I ask whether anyone else has another question for Lydie? Okay, so this is just it's a more philosophical question. When you said about the whether cohesion changes friction or not, I think it certainly changes the way that you dissipate energy, right? Because cohesion will enhance the normal force at which the friction force will be calculated, but it's not clear whether it changes the mu. That was your point, right? So the rheological parameter, which is mu, changes or not with the presence of cohesion. And then after this question, the question would be, in the continuum simulation, this excess stress that you add, the tau c, this cohesive stress that you add to your continuum does not enhance dissipation, right? Because it's not linked to gamma dot.
No.
So is that why you cannot compare the runout in continuum and granular and in discrete simulations? It would be difficult to match.
Actually, I'm not sure I'm not sure I understand the flow of cohesive material, actually. So the yield stress that is implemented in the continuum model is actually a classical yield stress. It's cohesive because it's a yield stress, and cohesive material have a yield stress, but there's nothing more than this is just the same as you would put in a Bingham.
Yep. Flow, fluid.
So yeah, exactly. So comparing it in the runout while the things are flowing, it seems comparing two very different things, actually. The continuum is really capturing the stability of cohesive material, but I'm not saying that it's really capturing the flow.
The flow.
No. For that, we would need to make to analyze the runout. The runout without cohesion compares well. I mean, we've done this before. We know it works. Once you've put this threshold, I mean, this yield stress, I'm not saying that it works. I haven't seen it. We haven't watched it. For the dependence of the friction with the cohesion, of course, the cohesion will increase the dissipation, but the idea, I mean, the underlying, the idea with studying the failure plane, the way the failure plane is defined and the way it is oriented and everything, coming back to Coulomb, is just this. I mean, if the cohesion affects the friction, the internal friction, this should show up in the direction of the failure plane.
I see.
That's the underlying idea.
I see. I get it. Okay.
Okay.
Very good. So I think we've any more questions before I say we are over? So I think we've asked many questions to Lydie. It's been a very, very interesting and productive seminar. So Lydie, let me switch on my camera. I can only thank you once again for accepting this invitation to give a seminar here for us in Brasilia. It's a great pleasure to have you. For those who don't know, Lydie and I shared we were neighbors, right? Office neighbors. A long time ago. I was going to say a few years ago, but then you said that a paper 15 years old is a long time. Then I am forced to say a long time ago because it was about 15 years ago. So yeah. So it was good times, very good times, and I can only.
So anyway, bye everyone. If you see me,
I think maybe we lost Yuri, right?
We lost Yuri.
We lost him.
Okay, so goodbye everyone.
Thank you very much, Lydie.
Merci
that was a very
beaucoup,
nice
Lydie.
talk.
Thank you for the talk.
Hi, bye.
Bye.
Yeah.